Okay, so I start recording. So um, um, hi, hi everyone. So I wanted to today to go over other forms of secret sharing, other secret sharing solutions, and particularly verifiable secret sharing. So it's what we have seen for now is different. So we have seen MPCs for honest but curious participants. GMW, YAO, and BGW for Boolean circuits, arithmetic circuits, and we have seen that general compiler from HBC to malicious participants in the form of coin toss to pick so randomness of all parties are generated the way they should be, and zero knowledge proofs attached to every message, and perhaps you can save on the coin toss if the underlying protocol has the property that it's secure no matter how you pick your coins. But we have seen that, for example, YAO is actually not secure. I mean, or at least like a standard way of garbling would not be secure here. Okay, now for the case of BGW, we have seen Pedersen VSS, which basically upgrades the Shamir secret sharing to verifiable secret sharing, right? And at what costs? So it's well, it's first of all, it required ON of group elements, reliable broadcast. So Pedersen VSS, what was it? We had two polynomials instead of one, and we used the other polynomial as so-called shadow polynomial, and used Pedersen commitment. So G to the M times H to the R, where R is the randomness in the commitment, to commit to all the coefficients of these polynomials, and that allowed, by homomorphism of Pedersen commitment, for local verification of every share against this broadcast of committed secret sharing polynomial coefficients. But we needed this reliable broadcast, and also everybody did this many exponentiations for each party, either to generate this secret share is this verification information or to verify it. Yes, and one round in optimistic execution, 3 rounds with false. So distributed protocols like this, you can evaluate their efficiency in the sort of default optimistic setting. So usual case, right, which means that there is no active attackers, things just go, and everybody's being honest, because if the protocol is secure against malicious participants, and there is sort of no rationale for cheating, they would be detected anyway and eliminated, right? Because not only you can detect any cheater in the system, but that would mean that, well, somebody is being alarmed. Look, on this network server, there is either a virus, or this participant is just a dishonest, or there is a malicious code running on it, right? So there is really no point to do that. Nevertheless, I mean, you do want to have efficiency of like, okay, what happens with faults? But it's really these costs that are the, in some sense, more of a measure of how the protocol would behave in practice, right? So these costs can be, so reliable broadcast is a practical issue, not so cheap to implement in a wide area network. And so exponentiations, well, it depends, right? Like if we have to do this cost per every gate, as we do in BGW, right? For every mult gate, you perform a secret sharing, right? In BGW, because you multiply each share, the two shares, right? And then you have to secret share that product, and right, and we reconstruct the secret sharing of the product of the two secrets. So if you want to use VSS at that point, right, like that means that now you do O(n) exponentiations actually for each sharing. Now, if you recall, in that solution, everybody shares. So now this jumps to n square. That's going to be not a pleasant cost contribution. Okay, so there is, you can say, two questions, or at least many, but is there alternative VSS solutions that would maybe somehow avoid these reliable broadcast assumption and drive down this cost? And a more specific question for BGW, can we skip the VSSs at each mult gate somehow? And there is a very cute idea for this, which influenced the practical development of MPC, both for BGW and for and for protocols that are formed. Maybe they're not explicitly BGW, but there's variants of it. And the idea was due to Beaver, and the idea is that you can pre-share verifiably. So do all the expensive costs at the beginning of verifiable secret sharing, and triples, so-called Beaver triples, A, B, and C, such that C is the product of A, B in the field. Okay, that the BGW goes over. So, in other words, parties hold secret sharings of A, secret sharing of B, and secret sharing of C. Now, by the secrecy property of secret sharings, they don't, this reveals no information about the ABC values. And assume that your VSS at the beginning, that you have a VSS which would allow you to reliably secret share such tuples, plus the property that is to say you prove that C is a product of AB. Now, actually, this relates to a homework exercise now, I realize, because if you do Pedersen VSS in this phase, then you will broadcast as part of this protocol a Pedersen commitment to A, because that's the free coefficient in the secret sharing polynomial, Pedersen commitment to B, and a Pedersen commitment to C. And you will want to prove in zero knowledge that that these committed values satisfy a multiplicative property. That was exactly a homework problem. How to extend these zero knowledge proofs, which are which handle homomorphic one-way group homomorphisms to the case where the witness is a vector of preimages in this homomorphism. So you think of this as discrete logarithms, and the statement, the image, is the image of these, so result of exponentiation. And you want to, in addition, prove that these committed witnesses satisfy some additive properties, like witness 1 is the sum of witness 2 and witness 3. But then the question was, how about the product? Okay, so that's exactly where you would use it. I mean, one example. Fix this. Okay. So, and the Beaver Triples idea was during computation of the multiplication gate, each party has values like xi and yi, which are shares of inputs to the mult gate, and zi, which is the product of these two. So it's the, okay, and instead of VSSing this product and proving that Zi is the product of these, and if we use Pedersen commitment, then this is Pedersen committed, because every share is by homomorphism of these commitments, you can reconstruct a commitment to a share from the commitment to the coefficients of the polynomial. And so is this one committed, right? Because it's an invariant for every secret polynomial, secret sharing of every gate that is true. So there is a public commitment to this share, there's a public commitment to this share, and now this party is VSSing the multiplication, right? So for committed xi and yi. So instead of doing this, can PI utilize the VSS of A, VSS of B, and VSS of C, which is a product, to cheaply create VSS of Zi, which is xi times yi, given basically the VSS of xi and VSS of yi. Okay. So I'm not going to go over this solution, but this is the kind of efficiency improvement that is very sweet in cryptography. You do the expensive stuff in pre-computation, and you use some arithmetic properties to save in online computation. The intuition is because this is okay. So here is the intuition. You can convert this sharing. You can convert this sharing to sharing of this by broadcasting some additive shift between these values. And by homomorphism, now everybody can from this sharing, they can create this one in a non-interactive way. That's a very high level intuition, and of course, you know, as I said, you can not be sure like how can this be done, but well, okay, it's not super hard. You can work out how to do this or look up somewhere. Okay. So this is indeed how any MPC would do it in practice. Any implementation would do this. It's also, you know, possible to assume that so you shifted the online cost to the pre-computation. The total cost you haven't really reduced. Okay, because now everything is done in pre-computation. The expensive stuff is done in pre-computation. But there is applications in which the pre-computation you can, you know, it makes sense to assume that nobody cheats during these, or you know, it's not uncommon to have some secure initialization in systems, and yeah, okay. So another thing is that in a pre-computation, first of all of this can go in parallel, right? So the if you know how many mult gates you have in a circuit, right, or 10,000 mult gates. Okay, so you can generate all of them all at once. So there is already benefits to batching and pipelining and so forth. There is, and now you can also ask, okay, you know, is there perhaps a way to generate them all in a batched way that is more efficient, which is also not, you know, it's something, it's a separate problem. Okay. But the one thing that is, so this trick basically reduces the costs of online computation in BGW, you know, variants of MPC. but it's still what it reduces it down to is a single. It's still a round of interaction. Okay, everybody has to broadcast and send to everybody else. Basically, form of like resharing of these multiplications of the shares. But at least, well, and in the basic thing, you still perform exponentiations to verify, and then there is still more work that shows that you can avoid these, and it will be related to an alternative VSS solution. So the idea for avoiding this exponentiation cost at every mult gate, so you still have a round, but can you avoid the exponentiation costs, is that perhaps you can save all the verification costs to the very end. Okay, and just verify in a batched way that the intermediary steps had to be done correctly, rather than verify per step. Okay, but let's look first at these alternative VSS solutions. So, one is so-called Feldman VSS. I mean, so-called because of the name of the inventor. And the Feldman VSS works like this. And as I prepared, I confess I didn't. I realized that I need more time to spend with this to reconstruct how it truly works. So I will give you basically, unfortunately, a sketch and not a full solution. So the dealer in dealing a secret X and the field element picks a random polynomial on of degree t on two variables, x and y, i.e. f of x, y is a polynomial on two variables, so its terms looks like xi times x to the I times y to the j for some coefficient aij, and these coefficients range from 0 to t, so there is t plus 1 square of them. And this is all computation over the field. And it's a random polynomial subject to the constraint that at the 0, 0 point, it evaluates to x. So it is a two-dimensional generalization of some Shamir secret sharing. And you can think of the polynomial at f of x at 0. So think of fx at 0 as Shamir secret sharing. Sorry. So x is here. Let me change this variable, right? Because x is a free variable in the evaluation. So let the secrets that is being shared, let this be denoted as okay, and x is the variable in the polynomial. So f at 0 is the Shamir secret sharing of secret S. Okay, So the dealer picks this two-dimensional polynomial, and he sends a secret. So he picks the polynomial and sends to each PI share, I guess, SI hat, which is a vector of the following things. So the SI j value is the evaluation of the polynomial on ith point and jth point, and that he gives to this to PI for every j value in the range. So I need the notation, and is a set of all indices of the n players, right? So what this implies, if you get the ith guy gets the value of this polynomial at point I at every other index, this is now, so along this dimension, it's a t-degree polynomial, right? If you fix I and evaluate the different j's, it's a t-degree polynomial along, that is defined there. This polynomial can be denoted this way. Okay, it's a t-degree polynomial, and essentially PI gets that polynomial, meaning he could just as well get the coefficients of this polynomial. Okay, it's the equivalent. In addition, so in particular, he gets Fi at 0, right? I mean, J goes from 1 to n, but he can interpolate that to get this polynomial, and he can evaluate that to compute this value. And now, so this is like a standard Shamir secret sharing share if f this is you know of this polynomial of this polynomial, right? It's this polynomial evaluated at PI's point I, right? This is the standard share if this is the secret sharing polynomial. What do we need all these other points? Why do we you know interpolate? Why do we sort of create this other dimension? So this, what used to be a share in Shamir secret sharing, now became a whole polynomial along the y direction. Well, PI will use this as verification that this share, that this is the real share that he cares about, is dealt to him by a potentially dishonest dealer in an honest way. And in order to do that, he okay, so in addition to these values, he also gets the following values. Again, for j, all j's. Okay, so he gets this vector and also that vector. What is this this information imply? It implies basically this polynomial, okay, which is also a t-degree polynomial. So it's the polynomial where I is fixed, and yeah, the y value is fixed, and now x varies. Graphically, it looks, you can see it is like this. So here is the f x0 polynomial, and here is the secret, which is f of 0, 0. The value here is the standard Shamir secret share of P1. But what P1 gets is the polynomial f, hold on, f1, okay, so this polynomial is has the first argument x fixed, and it varies over y's. And in addition, he gets, let's call it like this, right? So the y is the variable here. And this polynomial is f(x1). So this is what the P1 player gets, these two polynomials. In general, PI, right, will get f this polynomial and this one. Okay, so PI's share is this polynomial and this polynomial. Now, to verify that the dealer sent this share honestly, okay. So this is what these players will do. PI sends to each PJ value f ji. So this is this value PI sends to PI plus 1. This value PI sends to PI plus 2, etc. Okay. So now let's look at it from sense value, this one. So this was denoted here as Ji. So now, what does PI receive, right? So let's think of P1. Well, he gets this value from PI. He gets this value from PI minus 1, and this value from PI plus 1, and so forth. So he gets this line. So let's move to PI. He gets all these values, right? So PI gets values, and let's call them Sji hat from Pj, and that's for all j. right? Without loss of generality, some of them might not send any value at all. Let's just consider that as like sending a 0, okay? There is, even if we don't have broadcast, there is an implicit assumption here that communication goes in rounds. That there is a round that says you're supposed to be getting values from other players. In practice, what if you don't get any value? Should you wait till you get it, or should you time out and continue computation? Now that is a difference between synchronous and asynchronous communication model, which makes a huge difference here. If you assume synchrony, protocols like this, right? Like it's much easier to write the code and easier to argue about, that some subset of bad players here cannot cheat. Once you have asynchrony, which means the following, that basically messages can be delayed by arbitrary amounts. Okay, so you cannot wait forever. At some point, you have to gather the messages that you have received so far and make a decision based on those. Now, these protocols will their time will depend on how much the adversary delayed all the messages. That's unavoidable, but they will have a liveness property, which is that the communication will eventually complete, and that if enough messages go through, then the protocol will complete. Now it will complete perhaps by everybody rejecting everything, so that's still not, that's not all you want. What you want is that at the end, adversary cannot, make them reject an honest secret sharing just by delaying it, right? So Feldman actually has it achieves VSS in asynchronous setting, and the arguments for why it works are harder, but it does achieve it. And I forgot the threshold that you require for it, whether it tolerates a third or a fourth of the malicious players. Okay, so PI gets values like this from other players, and well, he got some version of these values from the dealer, right? So, and basically the whole thing is about, and let B be the set of indexes J, such that the verification value, like for example this one, it's S1I is a value that player I received from the first player, right, who got this polynomial and this one, and this player P1 sent all these values as verification values to other players. So in particular, PI received this S hat 1I from P1, but he also received S1I here, right? He received this whole line from do I have the
I think you need to switch it.
And yes, right. I didn't get this correctly. Yes. Right, because the PJ gets JI. So PI gets IJ, and right, is so let B be the set of problematic. So PI gets this line from the dealer, and also he gets this line, points on this line from other players. And the reason for broadcasting, for getting this variable from other players is so that PI can decide whether the dealer cheated him. So let the set of values that indices where the verification point he received from player J is different from the share that, so this is the verification point from PJ, and this is the point received as part of the original sharing from the dealer. Okay, and now, okay, let's say that some subset B is wrong. There are two possibilities. Either the PJ who sent me this share is trying to cheat me. The original dealer was honest. He gave me the right stuff along the whole line. But some other bad person in this whole group is trying to dissuade me from accepting this sharing and mess me up by sending the wrong verification point. So that's one possibility. The other is that the dealer was dishonest. He either gave me wrong points on this line, at least for some of them, for those in this set, or he gave me correct ones, but he gave the wrong points to some player J, right? And so this poor PJ, of course he sent me the wrong verification point, right? Because he got the wrong line here. So the whole thing is about now if the set has more than T elements, then I know that the dealer must have been dishonest. Because if there is only T is the number of max number of cheaters, okay, in the system. Okay, so if the set is larger than T, then I know that the dealer was wrong. At that point, as in Pedersen, I can send my whole polynomial. I can open up, right? Because I know that this is a cheating player. So there is no secrecy property to all these shares that I got. But if this set is smaller, then yeah, then it's still a question of is the dealer cheating me, or are these players cheating? And at that point, basically, there is Feldman has a reconciliation procedure, which yes, which allows people to distinguish these 2 points. I mean, these 2 cases. Yes, and I basically confess that I have I don't remember how this works, and I ran out of time to prepare, so I don't remember how this how this reconciliation really worked, and the way you reconstruct is that you publish both lines. One thing I guess is so first of all, like, why is it secret, right? So what do the bad guys get, right? They get basically like a quadrant of these functions. They get t of the vertical functions and t of the horizontal ones, but there is but this value is still independent of that information. In a right, like so you can see, okay, getting all these values, right, it just gives you t values on the line, and getting these ones is still, every choice of the secret would define a polynomial that is consistent with the lines that the bad guys get, and therefore information theoretically this value remains secret. These verification vectors still don't change that secrecy property, right? If the dealer is honest, all you are sending is values that this person already has, and they get something new only if somebody was cheating, but by that token, something that is inconsistent was already known to the attacker. The attacker must have sent it. So new information is not more information to the attacker. But the whole beauty, I admit, of this method is precisely why these verification points suffice to either disregard the cheaters or disqualify the dealer, and that I'm sorry to admit I did not clarify for myself before the lecture. Okay, so this still is a little bit question mark for you, but look, at least you see where a solution is coming from.
Professor? Could you get the paper back? Okay, so is there a reason to get such a big polynomial? Because it seems like you could get, instead of all these terms, you could get I plus j minus or equal to t. So it would be linear on t, the number of coefficients. Because right now it's quadratic, right?
Yes.
But I was trying to find where that was used, but maybe it's the part you didn't show us.
No, I think that then if you reduce the number of free terms here, then probably T lines will already reveal the secret, because basically each line here is T plus 1 plus T times T. Unknowns are revealed.
Right, yeah, you could fix
so there's like T plus square freedom. And how much each polynomial reveals? Well, T of T plus 1.
Right, because Y would be fixed, so you could find Aij.
Yes, so if you make correlations between these coefficients, it will probably attack secrecy. I mean, probably mess up secrecy.
Okay, I see it now. Thank you.
Yeah. Okay. So, well, it only works against smaller subset of so the set that you can tolerate is not a half. This argument basically, in some sense, like doubles the number of faults, and but with when this is sufficiently larger, and another thing that is used here is I think that you also have to use error correcting codes over these lines. So if the evaluation points are not 1, 2, 3, 4 all the way to n, but powers of a fixed point, then there is error correcting code solutions such that if you give me n evaluations of a polynomial on such indices, and 1/3 of these evaluations are arbitrarily switched, okay, they are wrong. It's a t-degree polynomial, so 2t plus 1 are correctly evaluated. T are wrong. Is there an interpolation procedure that would filter out the T wrong ones and interpolate, right? Because effectively the 2t plus 1 correct ones. There is enough information, so you can, there is an inefficient solution which takes every subset and interpolates and checks which one is correct. Okay, but right, and then determines like which 2t plus 1 define a t-degree polynomial and which ones are off. And so it eliminates the off ones and interpolates the remaining ones, right? But that's inefficient. If the evaluation points are powers of actually a root of unity in a field, then you can this test for correct versus incorrect is efficiently, you can implement it efficiently, and that helps in these arguments, because even if there is some subset that is wrong, you can still tolerate it as long as 2t plus 1 is correct, because then you can broadcast this in a reconstruction, and because okay, look at the final reconstruction step. Even if honest players are sort of convinced, okay, they got the good stuff, or they can ignore the bad parts, and the good parts are still define some unique share here, okay, because they do not know whether the bad stat is because of the cheating dealer or because the people who gave them these verification points were cheating. Okay, so if the set is sufficiently small, they maybe really, I'm sorry, but I forgot how Feldman goes exactly. It suffices that they have a 2t plus 1 good point because this point is well defined then, and so they know that the 2t plus 1 had the correct verification shares on those lines, right? Okay, then in a final verification reconstruction, the bad guys, in spite of anything that happened during the sharing, they can publish, wrong stuff here. And okay, and using this code, I can reconstruct nevertheless. But it's possible that actually Feldman doesn't need this because people, when they reconstruct, they have to show both lines. And now the good guys also have points on these lines, right? So the bad guys, if they broadcast completely wrong stuff, well, it has to agree with some lines that agree with the lines of the good guys. So perhaps those verification lines also suffice to eliminate those faults in reconstruction. Let me quickly point out another solution, which is it's used in the MPC with an optimal threshold. And well, in particular, okay, this could not be used. The number of players must be, greater than a third of the cheaters, and if you have a solution where which tolerates optimal threshold of n-1 cheaters, of course you would go for that, right? There is Rabin-BenOr VSS that is it's interesting as a VSS, but it also has a very an interesting tool in its guts based on so-called check vectors idea, and this idea is reused in places without the VSS that it was used for originally. So the check vectors can be thought of as a poor man's VSS, which eventually can be transformed into a VSS, but it's interesting on its own. Okay. So what's this poor man's VSS? So the dealer has a secret S, and he sends to the secret S to this to some party. We're gonna call it the prover, and think of S as a share during secret sharing. At some later point, there is going to be a reconstruction, and the question is whether this person who was given a share is going to publish the same share at the reconstruction time, or cheat and publish some other one. So let's say that he publishes the correct one, and V, the verifier, is any other player in the system, right? So if S was the share, then P is going to send his share to all the others, and everybody does that, so everybody gets all the shares, and then everybody locally reconstructs. In this application, V wants to check whether S, the share that P sent to him, was the same as that dealer sent. So the check vector's idea is that the dealer could send two, well, you know, we could give this, do it with the cryptography, right? Like perhaps this guy could, so here's how to, okay, you know what? Let me first show this solution and then talk about alternatives. So dealer will give something called a check vector to the verifier, and you can basically think of the check vector as a one-time MAC that is also information theoretically hiding the MAC'd value. This check vector is in their solution is a pair BC, and the dealer gave to the prover an additional value y. I'm going to call this thing, I guess, you know, it's a form of a one-time proof that S is correct. And when P publishes the share, he will publish this together with the, so this happens at the dealing time, I think dealing in secret sharing. And this is reconstruction for example, in secret sharing reconstruction, right? And V should have some efficient procedure that would use the check vector and this proof to verify that S was the same as the prover, as the P received here. How is the Rabin-BenOr solution for this? The dealer picked B at random. So assume S is in the field. Okay, assume it's in ZP P prime. So B was picked at random from ZP star, which is ZP without a zero, and Y is chosen at random in ZP. And C is picked as S plus BY mod P. V accepts if this verification equation holds, and rejects otherwise. And two properties. So first, secrecy. The secrecy is that the check vector BC reveals no information on secret S. Okay, and why is that? So if you have a BC in your hand, right? Well, Y was chosen at random. So here is for any possible value of S, you have B and C in your hand. And now let's say you're guessing what an S is. Well, unfortunately, for every choice of S, there is a choice of Y. There is a unique Y such that y is in ZP such that y is what is it, C minus S divided by B mod P. And now this is why B is not 0, precisely so you can do this for every B, right? Every choice of S gives you a choice of Y, and it's a different one. Yes, if the Y's would be the same for some two S's, this implies that this was the same S. Okay, so it's a C and B define a bijection between secrets and the randomness used in dealing, which means that the BC are information theoretic independent of S. So in other words, to see it is that BC are random in ZP star cross product ZP regardless of S. That's not how they picked, right? Like the first Y is chosen and then C, but you could invert and basically first choose C and define Y as using this equation, and you would generate the same YBC distribution, which now once you do the switch, you see that BCs are independent of S. Okay, and then the second property is of soundness, that cheating P can get V to accept some wrong value of S with at most one of the P probability, where P is the size of this field. Yes. So why is that? Well, because the only thing P has is S and Y. If he could predict what BC is, well, then he could cheat easily, right? Because for any S, he would just compute Y. So if he knew C and B of the verifier, then for any S prime, he would compute Y prime that satisfies this equation. The question is, what does he know about C and B? And so for cheating, it's the secrecy property in reverse. For secrecy, we are asking what information about S is given in BC. And for soundness, or for cheating in reconstruction, we are asking what information about BC is visible in SY. And not enough to cheat. So the cheating P, how can he accept? P has to send Y prime, which agrees with this equation. So it's C minus S prime. So if he wants to send S prime instead of S, he has to send this Y prime mod P, right? But as we said in the secrecy argument, but BC is sampled at random from distribution Okay, so there are samples that run from this distribution like this. Okay, and then P gets some information about the sample, and P gets the following information, Y, which is C minus S over B. Right, so this is the information he gets about P gets about the sample, the BC sample. But what does this information give him? Well, for every B, there is a unique C such that this information that P gets holds, right? For every B, well, the equation is this. P has S and Y, and now for every B, there is some C that satisfies this. So if P is successful, he needs to predict the C prime over B, C minus S prime over B value. But what he knows about C is for every, let's guess a B value, then C is equal to S plus YB minus S, well, and now we carry, right? So this is Y plus S minus S prime over B. P knows all these values, but he doesn't know this one, right? And every sample of B is possible. Every choice of B determines the proof that cheating P should supply to get V to accept S prime. But B is, from the information that the cheating prover has about B, is none. It's B individual is random in ZP star, right? So probability of P sending correct Y prime for S prime is equal to probability of guessing basically B, which is 1 over P. Okay. So yes, yes, because every B value is equally likely from his perspective. Okay. Note that this is much cheaper than anything. I mean, okay, so it's not yet VSS, but it is definitely cheaper than. We could do this in a more expensive way. Dealer could send to verify a commitment to S, and Y could be the decommitment, right? And then, by binding of the commitment scheme, the P cannot cheat in revealing, right, in opening a commitment. And by the secrecy of a commitment scheme, the check vector, which is a commitment, does not reveal information about the committed value S. So you get the same properties, except we don't know commitments that are as inexpensive. Okay. You can also, dealer could sign, right, this message and give the verification key to the V. Again, this is public key crypto, so it will be more expensive. It's a kind of an exercise. This is really a one-time signature scheme. And indeed, a one-time signature scheme had a very similar, the example that we gave in the basic crypto class was very similar. Cast this in a general form as an instance of a one-time signature, and you will get the same equation. This by itself basically gives you. I should be wrapping up. How do we get a VSS from this? So one is exactly the way we were justifying this, right? So let's here is a form of VSS. A dealer gives Shamir secret shares to all players, but in addition, for every pair of players, it gives a check vector. So let this pair of players be PV, okay? But this is basically PI and PJ, okay? For any n square choice of I and j. And if S is the it's the Shamir secret share of that P holds, okay? Then this BC and Y will be the check vector and a one-time proof for that pair of PI, PJ. So when PI reconstructs his share, he will have to, when he sends this share to PJ, he will have to accompany it by this one-time proof, and V will dig out the check vector that he got from the dealer for verifying PI's share. How many check vectors people have to get? N, one for each other player. How many one-time proofs? N, one for each player, right? I mean, so everybody gets one share, but N one-time proofs and N check vectors to verify all the other senders. This gives you kind of half verifiable secret sharing. Assuming the dealer is honest during the sharing procedure, so he created the shares correctly and he created these one-time proofs and check vectors correctly, basically assuming that you have honest dealing, the reconstruction is now resistant against cheaters, right? Because the only way cheaters can smuggle a dishonest share is by cheating by finding a proof, right, for a wrong thing, and this is information theoretic hard. So you have a VSS that is good for online computation, like you think of the BGW application, right? If you had the secure initialization, this check vectors would be all that you need. Okay, now the question, of course, how do you assure against a dishonest dealer? Well, so you're going to say, okay, you know what? It's the dealing phase, it's the initialization. Perhaps we can tolerate a more expensive stuff to generate the correct tuples of proofs and a check vector. But this paper actually showed that this you could verify dishonest dealers using the same idea of, it's sort of similar to Feldman tool. You can well, okay, you generate these check vectors and you can you know what, okay, I forget exactly, and now I'm going to just mess it up, but you can use this and open some of these and verify that the dealer is honest, and then with high probability you end up with a good one that you can use in reconstruction. Another thing about these check vectors, so but in the offline versus online, right, setting like in this BGW, this is a gain. Another thing about this particular thing is that it's these operations are also over the same, think of using this in BGW. If shares are shares of gate input, right? Shares of gates. And you have these one-time proofs and check vectors. If you have, the invariant, that for every gate, you keep on having proofs and check vectors. Let's say for everybody's share on that gate. Then using these homomorphic properties, perhaps think first of the additive gates. Perhaps you can non-interactively keep maintaining this invariant. So the proofs and the check vectors for input gates, when they input, where the gate is an add, and the shares S, the secrets on that gate, are added. Perhaps the one-time proofs and the check vectors can be added too. There is a mult here. But perhaps why on all values can be the same. So the proof is really why can be reused. So that's not apparent, but you could batch and use the same Y for a bunch of vectors. Yes, okay. It's not apparent, and I don't want to okay, try to reconstruct this, but yeah, if it's true, it shouldn't take much time to verify it. And I think it is true. And if you, so then the add gates, you can actually go from, you can maintain this invariant. Now, for mult gates, it's a a new question, right? How do you go from one-time proofs and check vectors for the gate inputs to the one-time proof and a check vectors for gate output? And you can, it's a form of a Beaver triple, but now not for the, I cast it at the beginning of the lecture as if for Pedersen VSS. Well, you can cast it for these proof check vector tuples. And so that perhaps if you have proof and check vector for Beaver triples, which is pairs of A, B, and C, which is a product of A and B, then can you, in an online way, in a relatively inexpensive way, broadcast something that is going to translate the check vectors for this initial ABC tuple to the check so that everybody can translate check vectors onto inputs to the mult gate to the check vector on the output of the mult gate. So that's indeed possible, and the MPC based on roughly the BGW idea, the BGW processing, and VSS where everything is done with these check vectors, and kind of Beaver triples to speed up the online processing. There's a line of MPC based on this, which seems to be well, the most efficient, but optimizing these the arithmetic circuit computation and dealing with malicious faults securely. Okay, so that's all I wanted to say about this. Okay. Do you have questions before we quit?
So we will have class tomorrow?
Yes.
Okay.
Yes. Okay.
Will it be at the same time?
Yes. 9:30.
Okay.
Okay.
Is this taking? Sorry, I think I missed the previous class. Is this taking place of Tuesday?
Yes.
Okay.
Like I said, I had some. Okay, I had to basically cancel the Tuesday class, and we'll do an extra one on Friday.
Sure. All right. Thank you.
Okay. Thank you, and see you tomorrow.